Okay, I think that we can start. I don't see any more message in the waiting room. So first of all, thank you for the participation to this webinar. Just an information note, this webinar will be recorded, so there will be available on our website, the Tough Steel website. In this way, if you have not the opportunity to follow all the webinar, you can review it offline when you want in our website. So today we will have two presentation. The first one from David from Meta that will introduce us what's the main aspects of the essential worker fracture and the advantages and limitation of these new methodologies. And after that, we will see a case study in which we compared the virtual simulation and the physical stamping, creating a correlation between these two aspects. Before that, I just would like to introduce briefly the Tough Steel projects. Okay. So the Tough Steel project is a dissemination project funded by the Research Fund for Coal and Steel within the Horizon 2020 program. Is a project with a duration of 2 years. It was started last year in July and will be concluded next year in June. We are 8 partners from 4 different European countries, and it is coordinated by Eurecat. Here you can see the partner where are located in Spain, Italy, Belgium, and Sweden. We are a very mixed partner because we have 2 universities, 1 research institution, 1 end user, 3 steel association, and 1 standardization company. The goal of the Tough Steel is to increase and share the knowledge about the essential worker fracture between the main actors of the sheet metal forming to increase and improve the use of advanced and stress steel, improving the efficiency and the competitiveness with the aiming to prevent any production losses and trying to reduce the lead time to have the product on the market. This is valid for the automotive, but not only. We are focusing also to the other industrial end user. Here just a very summary about the essential worker fracture that you will receive together with the presentation of today. But I would like to go fast in this slide because will be explained in detail by David very soon. So during the Tough Steel project, we will review the literature about this kind of methodologies, and we are working to collect and clusterize this information. We are preparing a database with detailed information about the material and the test that we have done in the past on the using these kind of methodologies. We are preparing a user guideline for the industries that will help them to use these methodologies in our daily activities. more high interesting for you is also the problem solving open call, in which we would like to involve 3 or 4, 5 industrial companies to show us their case study about the edge cracking, so the problems that they have in real cases, and together we would like to study if this kind of problem could be solved with the sensor work of fracture methodologies, or in other hand, if these kind of problems could be detected before. This to avoid to repeat the same problem in the future. We are doing several training workshop and webinars as today. And last but not least, we would like also to standardize this methodology, creating a specific white paper to have a standardized method for each partners and each stakeholder that could have a benefit using this kind of methodology. What are the expected impact? First of all, the material selection. So taking into account the EWF, there will be some information extra that can support the industries to select the best material for each application. We would like to predict and help the companies to predict the material behavior during the forming simulation in a better way to reduce the production losses. For sure, we would like also assess the crashworthiness of the material, and finally, we would like to reduce the time to market, and so give to the industries the opportunities to save money and time during the design phase. So now, after this short introduction, I would like to leave the speech and the floor to David Frometa, which will introduce himself, and after that, he will introduce us the essential work of fracture methodology.
Thank you very much, Michele, for the introduction and for this project overview. Let me share my screen. Okay, please let me know if you can see the presentation correctly.
Yes.
Yes, okay. Okay, then I will start. My name is David Frometa. I work as a researcher in the unit of metallic and ceramic materials of Eurecat. I'm the project coordinator of this tough steel project, which Michele shortly introduced just a few seconds ago. This is mainly a valorization project. It is called this fracture toughness as a tool to address cracking problems in forming and in service performance of advanced high-strength steels. This is the second training webinar out of 5 of them. And today in this presentation, I will talk a little bit about the essential work of fracture concept, about the main idea, what is a little of the theory behind this essential work of fracture to those who are not familiar yet with the method, and also mainly the advantages and limitations of the method, and mainly the main applications of the method to understand the fracture performance of these high strength or high performance sheet materials. This is the outline for the presentation today, divided into 4 different sections. First, as I said, a short introduction to the essential work of fracture concept. Then we'll see how to properly measure this essential work of fracture in thin metallic sheets, and then some different use cases or applications of the essential work of fracture methodology. And finally, I will finish with some words about this user guideline and fracture toughness database that Michele also presented briefly in the previous slides. Okay, then let's start by the beginning. To those, as I said, to those who are not familiar with the method yet and with the concept of the essential work of fracture, where this essential work of fracture comes from, where the origin of the idea. Well, this essential work of fracture concept is based on Broberg's idea, who suggested in 1975 and also in previous publications some years before, that the fracture energy involved in a ductile fracture process could be separated into two terms. The one is the one energy is the one developed in a small zone just ahead of the crack tip, which he called this end region. This is a small area ahead of the crack tip. And well, this on also it's also known now as the fracture process zone, which is the small area where the fracture mechanisms take place, and also an outer plastic work, so which in an area that surrounds all this fracture process zone. This first term, this essential work of fracture, which is developed in the fracture process zone, it represents the intrinsic fracture toughness of the material. That means that it only depends on the microstructure, so it doesn't depend on geometry, on the loading mode, the crack length, etc. So it is a material constant. Nevertheless, it is important here always to keep in mind that in the case of thin sheets presenting plane stress, like it is the case no, of the most of the thin metal sheet that we use, for example, in the automotive industry, ranging from 1 to 3 millimeters. These thin sheets presenting plane stress, this essential work of fracture is strongly dependent on the material thickness because it has a significant contribution from the work of necking, no? Which in turn depends on the material thickness. This essential work of fracture is, as I said, is represents intrinsic fracture toughness, and it is not an initiation quantity, no, contrary to the critical J integral value, for example, or JC, which is usually used to measure the fracture toughness of these ductile metals. And on the other hand, we have this plastic energy, you know, this extrinsic plastic energy, which, as I said, this is not a material property. It depends on the specimen geometry, on the loading mode, and so on. So if we want to know, no, we want to understand the fracture behavior and better understand what is the intrinsic fracture toughness of the material, we should somehow separate these two terms. Okay, but well, this is not easy. Let's see now how can we do it. Now let's see how to measure this essential work of fracture. As I said, this total work of fracture is composed of these two energetic terms, the one from the essential work of fracture and the one from the plastic work in an outer region, no, related to plasticity. It is important to note here that these two energetic terms are intermingled. That is mean it is difficult to separate them. Actually, most or not to say all of the fracture mechanics testing or testing procedures do not allow to separate these contributions from the essential work of fracture and from the plastic work. No? For example, the J integral, according to the ASTM standards, the J integral values are a combination of these two energetic terms. Now let's see how to separate experimentally these two energies. Well, by the end of the 70s, by year 77, Kotler and Redel developed this essential work of fracture methodology to experimentally separate both terms. How to do that? Well, taking a closer look to this equation, okay, this is the question that we saw in the previous slide. Taking a closer look, we can see that this essential work of fracture developed in the fracture process zone is proportional to the cross section. That is a work that happens in the crack plane. And while this non-essential plastic work is proportional to the plastic volume surrounding this fracture process zone multiplied by a shape geometry factor. This geometry factor, of course, depends on the specimen geometry. Then normalizing this equation and dividing by the cross-section area, we have this final form of the equation where we have this specific total work of fracture is equal to the sum of the specific essential work of fracture plus the non-essential plastic work, the specific non-essential plastic work multiplied by the ligament length and a shape geometry factor. Now, what's the trick to separate these terms? Well, the idea is to test a series of specimens with the same geometry, but with different ligament length. So we can scale this work of fracture. The ligament length is this area, this ahead of the crack tip. This is, we all always know, or usually put this as an example, this geometry, which is the double edge notch tension specimen, here being the ligament length, the distance between the two cracks or the two notches. We usually put this as an example, this geometry, because we have seen, and it's well reported in the literature, that this is one of the most suitable geometries for testing thin sheets. Well, as I said, with thickness ranging from 1 to 3 millimeters, for example, because is well, for flat, for these thin specimens is the most suitable because there's no buckling during testing, so all the stresses are tensile during the whole test, and also the all the crack is opening in mode one, no, during all the tests until fracture. But in principle, this methodology can be applied to other kind of geometries. So there's other type of specimen geometries like compact tension or this single edge notch bending specimens. In this case, we have successfully used also this specimen geometry, this single edge notch bending specimen, for example, for characterizing the essential work of fracture in thicker plates of high strength steels, for example, with thicknesses from 6 and 7 millimeters. In this case, so because with this kind of thickness and for very high strength steels, the use of this double edge notch tension specimens is, well, it's difficult, you know, because also the loads involved in the fracture are, are very high, and also to propagate the cracks is complicated. So this using this kind of specimens for thicker plates is much more easy. Then if we test these specimens up to fracture and we record this load versus the load line displacement, we have a plot like this, then we can evaluate the total work of fracture by integrating this area under the load displacement curve. As you can see here, with increasing the ligament length, we have, of course, the work of fracture, the total work of fracture increases. Then remember, we have the question here. If we normalize, or we divide this total work of fracture by the cross section, so by the ligament length and the thickness, we obtain an specific work of fracture. Now, if we plot this specific work of fracture as a function of the ligament length, we will obtain a plot like this. Here we have this specific work of fracture as a function of the ligament length for different ligament length. And then by making the linear data regression, we can obtain these two terms. The one is in the intercept, which is the specific essential work of fracture, and the slope, which represents the non-essential plastic work multiplied by this shape geometry factor. As I said before, this specific essential work of fracture is an average crack propagation resistance. Okay, so it is, as it's often said in literature, that it is equivalent to JC, but it is not strictly true. In some specific cases where, for example, where the contribution from crack propagation after initiation is not too large, maybe this JC and essential work of fracture could be considered equivalent. However, when we have an important contribution from crack propagation resistance, these quantities tend to differ. You know? So also interestingly, from this methodology, we can also evaluate an energy value or fracture energy for crack initiation. How to do that? Well, in this test, by using a high-resolution video camera or a traveling microscope or similar equipment, we can detect the onset of the crack initiation and also calculating only the energy up to this onset of crack initiation. In this way, we can obtain a fracture energy and a specific fracture energy for crack initiation. And if we plot these values as a function of the ligament length, as we can see here, we can see that contrary to that we observe with the total work of fracture, these initiation values are independent of the ligament length. So making an average of these values, we can obtain a fracture toughness at crack initiation. This is interesting because, well, sometimes there are some materials that this crack initiation of this essential work of fracture at initiation is very similar to the total work of fracture or the total specific work of fracture. So in this case, this essential work of fracture could be considered both an initiation and propagation. However, there's other materials with a significant contribution from crack propagation resistance, and this essential work of fracture is much larger to that than the initiation toughness. This is important to understand because we have seen that the value, the most suitable parameter to understand the overall fracture performance of this high strength or high performance sheet materials is the one considering the total or the overall cracking resistance, which is the essential work of fracture, as we will see in the next slides. Well, this is a very interesting method, especially for thin sheets, because, well, it's relatively simple. You don't have to measure the crack advance during the whole test, which is one of the main challenges of this fracture mechanics testing. So it's a simple test. You don't have to measure. You can test specimens up to fracture and evaluate these energies. So it was developed to evaluate the tearing resistance or the fracture toughness of thin metal sheets, but it has been also widely used in polymer films to evaluate the fracture toughness or the tearing resistance of polymer films. And in the last 14, 15 years, it has been also widely used to characterize the crack initiation and propagation resistance of thin, high strength and aluminum alloys and advanced high strength steel sheets. Well, unfortunately, for one of the main problems that hampers the wide application or more extended application of this method is that there is no standard method for evaluating the essential work of fracture in thin metallic sheets. Most of the works in the literature and so on, most of the works to the date are based or in a testing protocol, which was developed by the European Structural Integrity Society, which, well, is intended to the evaluation of the essential work of fracture, but it's more directed to polymers. So with this in mind, and considering the growing interest of the sheet metal forming industry in general to know about these fracture toughness properties and more specifically about the essential work of fracture, in a recently finished Horizon 2020 project, we developed together with different standard organizations and also important actors of the sheet metal forming this 10 workshop agreement, which is which is a proposal for normalization. This is like the first step towards the standardization of the method. This CWA is called Test Method for Determination of the Essential Work of Fracture of Thin Ductile Metal Sheets. You can find this document. You can download it for free on the internet if you look for them. And well, the document is intended to be a reference document to evaluate this essential work of fracture in thin metal sheets. So we explain the method, we propose different recommendations about the specimen geometry, specimen size, the notch preparation method, and well, all the experimental setup and different things. So it is intended to be a reference document if you want to measure the essential work of fracture in thin metal sheets, where you can have a look to this reference document. Well, now we have seen how to measure this essential work of fracture in thin metal sheets. Now let's see what this essential work of fracture is useful for. No? Why we need, or why we consider that we need to measure the essential work of fracture in general in thin high strength metal sheets. Well, first, some of the results that we have obtained during also several years of research in the field in the frame of different research projects and collaborations, mainly with steel makers, in projects related to the development and optimization of new advanced high strength steels. As we can see here, we observe from over these years that this fracture toughness, this essential work of fracture value, is a suitable parameter to rationalize or to predict or to classify at least this edge cracking sensitivity of very high strength materials. Here in this plot, we can see several values of Hall expansion criteria values for a wide range of advanced high-strength steels from 800 megapascals UTS to 1500, where we can see the very good correlation between the essential work of fracture and the Hall expansion ratio, which, as you know, is one of the parameters used to evaluate this strength flageability or this edge formability of sheet metals. Then, well, we have this fracture toughness. You have a material property that is really useful to understand this edge cracking behavior of high strength materials. This is very useful because, well, as you know, if you are familiar with the Hall expansion ratio, let's say the reliability of this parameter to evaluate this edge cracking resistance or the strength fungibility is often put into question because it depends on many variables. It depends on the whole preparation method and the cutting clearance, in the method for determining the crack on set, and so it depends on many variables. So the industry is constantly looking, for material properties that help to better understand this edge formability or this edge fracture behavior, which at the end, as we have seen over these years, is strongly governed by this crack initiation and propagation resistance, or by the damage tolerance of the material in the end. Something similar we observe with the crash behavior of high-strength metal sheets. We have seen also in different projects that the crash behavior of especially the axial crash behavior of high strength metal sheets, high strength aluminum and steel sheets, is strongly governed by formation by formation and propagation of cracks through the sample, during the crash test. This crack nucleation and formation strongly affects also the foldability material, which in turn also affect the overall crash performance and the energy absorbed during the crash event. So what we can see here in this graph is again values of energy absorbed at maximum intrusion, which I said they are closely related to the cracking degree of the samples during crash tests. So in general, these steel grades showing lower energy, showed a higher degree of cracking and a poorer foldability, which is translated in this poorer energy or energy absorbed at maximum intrusion. So here we can see again for similar grades to those that observed in the left picture. Similar grades, advanced high strength steel grades, again from 1,000 megapascals to 1,200 megapascals. So with very different microstructures, considering dual phase, complex phase, press hardened steels, TWIP steels. What we can see here is again the very good relationship between this crash behavior and the fracture toughness. What we could see here is that this this crash foldability, which is often measured at the small scale laboratory level by the bending test to assess the bendability, we have seen that this overall fracture behavior is not only governed by the crack initiation, which in turn is defined by this bendability, but also how rapid, let's say, these cracks propagate through the sample, which is governed by this fracture toughness, which is well represented in this case by the essential work of fracture. So here, the same, according to this graph also, what we can see is that we can determine or we can define different cracking resistance levels using this essential work of fracture methodology, and have a first estimation of the overall fracture behavior of this high strength, in this case, advanced high strength steel during crash. But also, we have shown that the essential work of fracture is a usable tool. It's a very useful tool, for example, to predict problems, or not to predict, but to understand problems of edge cracking during cellular production in the industry. Here, I put here a couple of examples. The first one is, this is a cold form component. This is the result of a collaboration that we made with CRF some years ago, also in the frame of a European project. In this case, this is an undersheet beam, which they were having several problems of edge cracking with the original material, which was a dual phase steel of 1,000 megapascal. Okay, so after investigating the material and see that all the properties and everything was okay, also within the certificates and so on. Then they solve, well, they decide to change the material. So the problem was solved by using a complex phase steel of similar strength level and similar thickness. And well, after studying the difference in the mechanical properties, the formability, and so on, well, we can see that from tensile properties and from conventional ductility criteria, the dual phase steel should behave better in formability than the complex phase steel because have had greater elongation. But as we know that this kind of edge cracking problems or focal formability problems are more related to the damage tolerance or the fracture toughness of the material, we could see here applying the essential work of fracture that the new material, let's say the complex phase one, was the one with a much higher fracture toughness, no? Which could help to understand this different fracture behavior during forming. Here, this is also a similar example. This is a case study that we performed in the frame of the recently finished form planet project that I mentioned before. In this case, it's with an aluminum alloy. It's a 5000 series aluminum alloy. Also, again, the customer claimed by a series of problems of cracking during conforming in a component. And to solve this problem, they had to replace the material by a similar aluminum grade, but in this case, it was called an OK because well, it was a reformulation of the alloy, in this case, to solve these problems of edge cracking. Again, when trying to understand the difference in the intrinsic difference in material properties to explain this different fracture behavior, looking at the tensile properties, elongation, tensile strength, and so on, it showed that the difference between two materials were not very significant or were they pretty the same. However, again, when looking at this essential work of fracture, we could observe the huge differences between the OK and no OK material. Okay, so here the message is that this essential work of fracture is a suitable tool to better understand how the fracture behavior of this high strength and high performance materials will be during cold forming. But we also have used this essential work of fracture, for example, talking about aluminum, in this case for assess or to assess the ductility level of aluminum castings. In cases where this aluminum has have a large ductility, where let's say where linear elastic fracture mechanics is not longer suitable to evaluate the fracture toughness of this kind of materials, we can also use the essential work of fracture to evaluate the crack initiation and propagation resistance of this kind of alloys. So it is a suitable tool, for example, for tailoring the chemical composition to see the effect of variations in the chemical composition or in processing parameters to evaluate the influence of these variations in the fracture behavior of this kind of materials. Also, we have seen that this is a very powerful and very interesting tool for microstructural design. In the case for the design of optimized or optimum advanced high-strength microstructures, to better understand the role of the different microstructural constituents, the distribution, the amount of phases, etc. For example, it is known that in advanced high-strength steels, it is known that these DP or dual phase-like microstructures, that is to say those which are those microstructures whose microstructure is mainly consisting of a soft or ferritic matrix with a different amount of different proportion of hard secondary phases embedded in the matrix. It is well known, as I was saying, that these 12-phase-like microstructures have in general a better global ductility than complex phase-like, where complex phase or CP-like refers to those microstructures being mainly pinitic or temperate or with temperate martensite. However, what we have seen also over these years is although these dual phase like usually have greater elongation values, as you can see black symbols here, then the trend regarding the fracture behavior or the damage tolerance of this kind of materials is rather the opposite. So We can see in the blue bar, for example, the essential Walker fracture for different complex phase-like and dual phase-like. And we can see that in general, these complex phase-like, while show lower elongation values, they tend to show higher damage tolerance and higher fracture toughness. And other specific cases, though, is the one of the trip-assisted microstructures containing retained austenite. It is well known also that this sustained transformation of retained austenite to martensite has a beneficial influence on the strength of ductility, especially in global ductility. As we know, it is known as this trip effect, okay, which contributes to improve the mechanical properties of this higher strength steel. For example, it is clearly seen here when we see the more the higher the content of retained austenite, the greater this UTS by total elongation product, which is usually used as an indicator of the global formability or the toughness of the material. However, when we look at the influence of this retained austenite content on the crack propagation resistance, we can see that there's no correlation at all, or even a negative effect, we could say, somehow. Then, if we want to find the optimum balance when designing these new microstructures, we want to find the balance between this global ductility and cracking resistance. It is important to have to take a closer look to these fracture toughness properties or to this essential Walker fracture. Also, here I put also another specific case where this specific essential Walker fracture was used to better understand the influence of microstructure on the fracture behavior of this kind of steels. In this case, it was on a study on two dual phase steels with 1,000 megapascal of maximum strength. In this case, the two dual phase showed very similar mechanical properties, as you can see here in this plot. You see the engineering stress strain curves. You can see the properties are very similar. However, they showed a totally different fracture behavior, totally different fracture toughness. So what we could see here in this work is that the importance of the microstructural constituents of the distribution, for example, in the case of a dual phase steel, of the distribution of these hard secondary phases within the soft ferrite matrix, also the hardness, the relative difference in hardness between the hard secondary phases and the softer matrix, as well the distribution. Also, we could see that these blocky martensite retained austenite islands, although it is well known, as I said before, that it has a beneficial influence on the global ductility, contributing to improve slightly this elongation. But we could observe that it may have a detrimental effect on crack propagation resistance. So what we have seen with these examples is it is a very powerful tool to understand this and to better understand the role of the microstructural constituents and for microstructural design in the end. Also, I put here some examples of how to use this, how we used in the past this essential Walker fracture methodology to discern also between okay and no okay materials to assess coil quality. The first example here, these are the results of a collaboration with a steel maker. Also, we also claim to have some problems in one of the coils, problems of local ductility when performing the bendability test and so on. And they wanted to better understand what was the main difference between the two coils. So what we did here was evaluate this essential Walker fracture also for both of the coils. What we could see here is not a large difference let's say in the average value, but we could detect this larger scattering in the no okay material. At the end, after the study and after some microstructural and scanning and electron microscopy observations, what they could detect is that in this case, this no okay steel had some problems with the inclusion level and distribution. So here's somehow we can detect with this using this large scattering the different fracture behavior of the different coils. Okay, well, as I said, although The difference in the total behavior in the total fracture energy was not that different. But we could observe is that the different population of material, no? Which is an indicator of there's something small or local microstructural inhomogeneities and so on. Also, a similar example is the one that I show here. This is also another case study from the Form Planet project. In this case, it's a C45 steel. This is a thicker plate of 5 millimeters. This is a C45 steel for fine blanking operations. Again, we have okay and okay materials. In this case, the no okay showed let's say not heterogeneous fracture behavior during fine blanking operations. So we wanted to see in more detail what was happening to this material, to this no okay material. After several investigations, the microstructure, make micrographs, and trying to find difference, the steel provider couldn't find any important difference on the two materials. However, when performing this fracture test with this essential Walker fracture test, which in this case we use single edge notch bending specimens because it's a thicker material, we could observe that in the case of the no key material, again, although we have similar case that even though the final value was not that different, we could observe also different population of also different data population, showing our more let's say less ductile behavior, or we could detect afterwards with analyzing these images at the microscope the presence of these quasi-brittle areas, or which were caused by let's say by local inhomogeneities, etc. So what we can conclude here is this essential fracture measurements are a suitable tool to predict this, these local inhomogeneities or this local microstructural defect, because you're very sensitive to them. So the fact of having here a crack makes this kind of test very sensitive to these small variations, microstructural variations, or heterogeneities. Well, according to this, or to all these examples, we have seen that this essential Walker fracture, we think this is a very powerful tool and very interesting to understand or to better understand all these kind of fractures related to the crack propagation resistance of these thin high performance sheet materials. So according to this, we recently proposed this alternative classification diagram, let's say, where was similar to the one proposed by Hans, where they use the true uniform strain to evaluate let's say to classify the global formability, and the true fracture strain to evaluate local formability. We proposed this similar or alternative diagram when we measure global formability in terms of the uniform elongation on the cracking resistance or the crack propagation resistance in terms of this specific essential Walker fracture. Now, from this diagram, what we can see is that well, we can define different levels of global formability and cracking resistance according to these two parameters. So, well, here, what also we can see that also, as I mentioned before, unfortunately, the trend is usually the contrary. So the steels with higher global formability usually or tend to have a lower cracking resistance. But now the challenge is to find this balance between formability and cracking resistance. So we should look to have materials in these areas where high formability and high crack propagation resistance. Also, alternatively, in a similar line of ideas, we propose this alternative classification diagram, alternative to the traditional banana plot, where these advanced high-strength steels are classified according to the tensile strength and the total elongation. Okay, so as we know, well, as we understand the need of knowing this crack propagation resistance of these kind of steels, we propose this alternative classification map using also the tensile strength, but we're using in the y-axis the essential Walker fracture. So to have a more comprehensive description of the overall formability and cracking resistance. And we can see here also this diagram is also very useful to separate or to group the materials according to their microstructure. Finally, let me finish this presentation with some words about this user guideline and fracture toughness database that we are elaborating in this Tough Steel project. Is that were briefly mentioned by Michele in the introduction. First, this these are two of the main results of the expected results of the Tough Steel project. The first one is the elaboration of a user guideline. As I said, when in this guideline we compile all this information. So all of the examples that I shown in the presentation here today are all compiled in this user guideline, as well with different recommendations about fracture toughness testing and thin ductile metal sheets. We explain the different methodologies from J-integral, essential work of fracture, cantier test, and also alternative parameters like the crack tip opening angle or this crack tip opening displacement or delta 5. As I said, we explain a little bit about these different methodologies, the main advantages and limitations of all of them. And also, well, the idea is not also to have also say a basis, no, or a guideline with a recommendation to the industry to better use this essential work of fracture or these fracture toughness measurements in the industry. Also, this document is the base, will be the base for a new 10 workshop agreement that we are planning to develop within this Tough Steel project, and also which will serve as a complement of the 10 workshop agreement that I presented before, the one for evaluating the essential work of fracturing in thin metallic sheets. Finally, also the important results or the important outcome of the project is the elaboration of this open access fracture toughness database, where our aim is to compile all this fracture toughness data of thin metal sheets, specifically. So mainly is essential work of fracture values, but also other fracture parameters like the JC or other values that we could found in the literature, and also with results from previous research project and so on. The fracture toughness database is being elaborated by the University of Louvain, and you can find this is the link where you can find this fracture toughness database. This is an example of the flow chart. So you have the possibility of create an account with an email and a password and organization, and you can either create a new entry. This is to input some data of fracture toughness. Following the steps, the platform will request for different information like chemical composition, microstructure, basic properties, and so on. But there's also the possibility of access to the database for consulting, to search or to get these ID cards to create maps of the fracture toughness against the thickness or against mechanical properties. I put here an example of a material card, for example, for a complex phase steel. This is some of the information that you can find in this fracture toughness database. This the composition, microstructure, different osteoplastic properties, mainly tensile properties, other parameters related to fracture, and also this fracture toughness, essential work of fracture, JC, etc. And as I said, also there's the possibility of generating this material chart using to classify the materials according to the cracking resistance and different mechanical properties. As I said, well, I don't know if I said it before, but all this user guideline and this fracture toughness database will be mainly available through our project website. So the user guideline is already elaborated, but we are now working on let's say in a more fancy layout to make a public document. It will be available in the project website soon, as well as the fracture toughness database. That's everything from my side. Thank you very much for your attention, and well, I will be happy to answer your questions, if any, by the end of this webinar.
Thank you very much, David. I propose to start with the second presentation of today, due to we have just 10 minutes. If you have some question about what David showed you before, you can write in the chat, and at the end of this presentation, we will answer to your question. Okay, so you should see in a presentation mode. Do you see the screen, David? It works correctly?
Yes, we can see it.
Okay,
Yeah.
okay, perfect. So for from the presentation done before by David, we have seen that the essential work of Fractal give us the possibility to see if the material is suitable or not for the local formability, so to be strange flanged, and for sure to avoid any crack during the stamping phases. But is a very is not only to check at the end, as we have done in tough steel projects, tough sheet project in the past, something at the end of the history. So we had a problem in the production with the P1000. After that, we changed the material in CP1000 and we solved the problem. But these create us costs. So we have lose the productivity and so on. We waste the material and we lose money. So for this reason, together with the partners, we are working to find the way to predict the behavior in the simulation phases, to anticipate the problem and finding the solution during the simulation and not at the end of the story. This is why we worked together, Eurecat, to try to introduce in the simulation a new information about the edge cracking to better predict the edge cracking phenomena. For this reason, we have done stamping trials using the T-node geometry, and in parallel also a simulation on this geometry. Why we choose the T-node? Because it's representative of the B-pillar component that is a critical component during the stamping phase, and not only because the B-pillar is one of the most important component during the lateral crash of the vehicle, and have twice have two behavior that have to satisfy. The first one to absorb the energy during the crash, and the second one to limit the intrusion during the crash, to safeguard the space inside the vehicle, and so to save the life of the occupants. So this is why we choose this component. The material selected was the TB, the trip by knitting 1180. This is why we selected this material, because is in first of all an innovative material, and second, this could give us the opportunity to reduce the weight of our component, because together with high strength of the material, because 1180 is the minimum tensile strength of this material, we have also a better formability compared to the classical DP, so dual phase grade. So it's a very interesting grade, and we believe that this grade could allow us to save weight in the new component for the new vehicles. On that, we have studied different shapes of blanks to make the stamping of the component. This because we would like to enhance the edge cracking during the stamping phases. We focus our attention to two different geometries, the rectangular and the trapezium one, with different shapes. On that, we have carried out the simulation considering two models. The first model taking into account only the forming limit diagram as a damage criteria, while the second one combine the FLD plus the essential work of fracture. On that, Eurecat performed the simulation with different geometries, with different blank holder force and so on. And at the end, we have chosen two ways to stamp this component. The rectangular one, that is in which the blank is positioned under the die, as you can see in the picture. These could help us to have more force in the blank holder during the die, during the stamping, and so this enhance the edge cracking. And at the right, you can see the simulation results. At the top, the model that consider only the FLD, while the bottom, the FLD plus the essential work of fracture. For the model in which there is only the FLD, we have the first cracking of the component at 11.55 millimeters of deep. While if we are taking in consideration also the essential work of fracture, we can see that the crack start after 10 millimeters and grow at 11 millimeter of depth. Same discussion also for the trapezium one. We compare to the two simulations in which we see that, no, sorry. Okay. In which you can see that the edge cracking start at 13 millimeter of depth, while if we consider the essential work of fracture, we have the first crack near the 12 millimeters, and after that there is a growing. With these results, we tried also a physical stamping of the component. These are the results for the rectangular shape, in which we can see that the crack appear in the area predicted by the simulation. So this is a good result, first good results. And also we see that the crack appear between 11 and 12 millimeter of depth. So these tell us that the new model that taking into account also the essential work of fracture is a little bit more conservative than the FLD ones, but considering the length of the crack is more similar to the models in which we took in consideration FLD plus the essential work of fracture. So is more near to the reality. Different behavior for the trapezium shape, in which both the simulation predict the edge cracking and the cracking in the middle of the blanks, but in reality we haven't any cracking. Also, if we consider a very deep deformation of 22 millimeters. For this reason, we have to investigate more on this simulation. These are just the first results. Moving the blanks under the die, and so moving up to permit to the blank holder to increase the force and bring stopped the blanks under the die, we found the edge cracking also with this shape. As I said, these are just preliminary results, but we would like to investigate more and to set up more this simulation to be a powerful method to predict the crack also virtually. So in conclusion, we can say that there is a fast and easy method to increase our knowledge about the sheet metals. We could have the possibility to determine in advance the cracking problem during the material usage, but for the simulation we have to work on, to calibrate more in the proper way the method to predict better the behavior. This is just the first results that we achieved, but we are proud on that, and we would like to start to share with you for sure in the near future when we will be when this result will be more consolidated. We will present you as a step 2 of this activity. Finally, just a key message: if we consider the essential work of fracture during the simulation, we can select the best material for each application, and we can avoid to spend money to solve the problem that we discover at the end of the story during the production phases. I would like to conclude my speech because the time is over, just giving you 2 new appointments. The first one is about the application of fracture toughness in sheet metal forming that will take place online as this webinar, the 12th of May, and you can see the agenda and the registration link in this presentation that will be available on our website. And the second one is an industrial workshop about the application of fracture toughness, material characterization, and modeling approach. These will be hybrid, in which you have the possibility to join online with the registration link that you could find in this presentation, and you could attend also in Stockholm physically. You will receive more information about this event later on our website. Is planned to be done the 7th of June. So that's all for my side. I would like just to check if there is some question. I think that there is no any question. Anyway, in both the presentation you could find the email address, mine and from David, and if later you have some question, doubts or curiosity, you are free to write us, and it will be our pleasure to return you our answer.
I think, Michele, sorry, I think there's one question. There's
okay, sorry.
Someone raised the hand. I don't know, Ivan, could you turn on the micro and to Ramin?
Hi,
hello, Ramin.
Hi.
Oh.
I'm very curious about the result. Actually, I know that it's 11 o'clock now, so we passed the time. At page 8 in your presentation, actually you show the results what Eureka had done during this project in practical way. If you go to page 8 in your presentation, so you compare the result from the real world with the simulation part, and we can see that directly you can predict instability at the edge of the product, and you can see you have the from simulation 1 between 11.55. But from the simulation side, you can see instability in those other areas, but you cannot see in the prototype you pressed in reality. How we can be sure that the simulation can predict instability and we cannot see in the reality?
Yeah, thanks for this question, Ramin. This is, as explained, just the first loop of the simulation. During the trials, we have seen that, for example, if we increase the depth of the stamping, we found also the cracking in the other areas that were predicted by the simulation, but
Okay.
not at the same level of depth. On that, we have to understand more with EURECAT if this is a problem due to the simulation, or due to the cracking of the areas, something change under the die.
Excellent. I believe that they should not run and symmetry part. Actually, they run as a symmetrical boundary condition for the simulation. I assume. If we go
Yes.
back to page number 10, and it's the same things here. Page number 10. Yeah,
okay.
exactly. That in reality, you can get instability for one side of the product if you made this test 10 or 15 times. Is it possible you can get instability in left-hand side or right-hand side of the product?
Yes. Yes.
That's
we
that
already found these results. This is just an example, but we stamped several blanks, and
okay.
sometimes we have the cracking just in one at the left, sometimes at the right, sometimes both. And I think that this is something also correlated to the shape of the blanks, because
Okay.
we don't have every time the same clearance, let me say.
Good, good, good. That's something again that we should run the full model, not only the access symmetry model for this type of product, because you have actually an access symmetry product, but the behavior of the instability can be changed from one
Yep.
side to other side. Thank you very much. That's a very excellent job you are doing.
Thank you, Ramin.
Okay, now I think there's no more questions, Michele.
Okay, so I would like say thank you to all the participants. I hope that you enjoy this event, and we will share soon with you by mail, by our website, and also you can find the link in my presentation for the next one that will follow this trend, and we will keep you updated about the new results that we will get time by time.
Thank you.
Thank you very much.
Have a nice
Goodbye.
day. Okay.